and welcome to this Hello, this is Steve Smith, and welcome to this Pluralsight video on one of the software fundamentals, the single responsibility principle. We'll begin by defining the single responsibility principle, demonstrating what some of the problems are when classes have too many responsibilities, and then we'll look at an example in code that shows how a typical e-commerce application might be worked out that exposes a problem with responsibilities. We'll refactor this sample application to apply SRP, making it so that it has a better and more maintainable design, and then we'll describe some related fundamentals that you can look to for additional learning. The single responsibility principle is defined on Wikipedia to state that every object should have a single responsibility, and that responsibility should be entirely encapsulated by the class. Robert C. Uncle Bob Martin, who's a very well-known author and speaker on these topics, sums this up as saying there should never be more than one reason for a class to change. This motivational poster describes what happens when an object has too many responsibilities in a great way, and how that affects the usefulness of the object. Take the pocket knife. This particular pocket knife has been extended to the point where it can do nearly anything except maybe fit in your pocket. And as the poster demonstrates, just because you can doesn't mean you should. And that applies to our software design of our classes as well. This relates to the concepts of cohesion and coupling. We want to strive for cohesion, but also for loose coupling. So cohesion is basically how strongly related and focused the various responsibilities in a module or a class are. And coupling is defined as the degree to which each program module or class relies on each of the other modules. Again, we want to strive for low coupling but high cohesion. Responsibilities are defined as axes of change. Requirements changes typically map to responsibilities. The more responsibilities a class has, the more likelihood of change. Having multiple responsibilities within a class couples together these responsibilities, making it likely that changes in one responsibility will affect or break features that are the other responsibilities of a class. The more classes a change affects, the more likely the change will introduce errors into our system. Thus, it's important to try and craft our classes in such a way that the areas that are most likely to change are encapsulated into separate classes with single responsibilities. Let's move on to a demo that shows the problem with too many responsibilities. First, let's look at a simple example from one of Uncle Bob's articles on the single responsibility principle that demonstrates the issue. In this UML diagram, you can see we have a class rectangle, and this class rectangle has two operations. One called area, that will return back the area of a given rectangle, and another called render, which will actually draw a rectangle onto a graphical user interface. Now, the render operation depends upon a GUI library, and you can see from this diagram here that it's depending on this library here for the GUI operations. But the rectangle itself is being used by two different types of applications. The first is a simple geometry service that encapsulates various types of operations and has no front end, no graphical user interface. And so it's only calling the area method on this rectangle. The other is a graphical application that might make use of the area method, but is primarily going to be drawing rectangles onto the graphical user interface that it too depends upon. Now you can see from these responsibilities that rectangle is now being used by geometry service, and geometry service will therefore have a dependency on this graphical user interface. If the graphical user interface changes, that will require rectangle to be recompiled and ultimately geometry service to be recompiled, despite the fact that it has no knowledge of or any concerns about graphical user interfaces or rendering. An improvement to this design would be to split the rectangle into two classes, one that was only concerned with geometry and calculating areas and such things, and another that was concerned with actual drawing or rendering of rectangles on a screen. Looking at a more business-oriented example, we have the concept of an order. An order, in this case, is defined as what happens when a cart is taken from a user's cart on a website or actual physical items at a point of sale store, and the order is placed. They make their purchase. They check out. And the order in this case has a number of operations that it supports. It supports checkout, it can also charge credit cards, it can notify the customer, and it can reserve inventory so that online orders can verify that the inventory is available before the card is finally charged and the order is processed. Let's look at the code for this order implementation. You can see that most of the work is done in the checkout method, in which we are going to see if the payment method is a credit card, then we're going to charge the card using the payment details that were provided. Once we know that this has gone through, we'll reserve the inventory from our inventory system. And then finally, if the customer has requested that they should be notified, we'll notify the customer that their order was processed. The rest of this class simply demonstrates some sample code that would perform these responsibilities. In this case, the customer notification is depending upon using SMTP email. The inventory is using this inventory service that's being newed up here within this method. And then, of course, the card charging is using a payment gateway and passing in some information to actually charge the card. So what's the problem with this design? Well, there are a number of problems. First of all, you can imagine that a point-of-sale application in which a customer is checking out items right there at the store, perhaps using cash, is not going to need to know anything about credit card processing. Point-of-sale transactions also don't need to be concerned with inventory reservations. There's not going to be a back-ordered item if the customer has the item in their hand when they walk up to the checkout register. And we can assume that the store inventory is being updated separately in our system. Likewise, the point-of-sale transactions don't need email notifications because the customer doesn't provide it, and of course, a customer in a store knows immediately whether or not their order was successful. Unfortunately, with this design, any change to the notification logic, the credit card processing, or the inventory management will affect order, and thus will also affect the web and point-of-sale implementations of order. So how can we refactor this to a better design? The first step in refactoring our application is to identify the responsibilities that are likely to change. In this case, we can see that the three things that our checkout method are doing is processing payment, reserving inventory, and sending notifications. We can break these out into separate interfaces as seen here at the bottom, where we have a payment processor with an operation for processing credit cards, a reservation service that can reserve inventory, and a notification service that can notify that a customer order has been created. Then we can take the order class and break it up into smaller classes that have fewer responsibilities and only use the interfaces that are appropriate for them. So for example, we might identify an online order which is created on the website, and the website only knows about online orders, as you can see from this new UML diagram with the dependencies shown. The online order makes use of all three of these interfaces because it has to do credit card processing, reservations, as well as notifications. However, the retail point of sale can work with different order objects. In this case, there could be a point of sale credit order, which would still know how to process payments using this shared interface, or the point of sale cash order, which would not have any dependencies on any of these interfaces because none of them are concerns of a cash transaction at the point of sale. If we look at the code to see how this is done, we'll see that we start now with an abstract class order that takes in a cart, since most of the operations we're working on are cart, and exposes a virtual checkout method that, for the sake of argument, we'll say logs the order to the database as part of its processing. Then the online order will go ahead and make use of these interfaces and new up a payment processor, reservation service, and notification service. And then you can see that its checkout method looks very similar to the one we started out with, in which we process the credit card, reserve our inventory, and then make a notification to the customer. A separate class for point-of-sale credit order will have only the dependencies and responsibilities that concern it, in this case the payment processor, and so its checkout method will merely do payment processing and of course the base checkout. And we see that the point-of-sale cash order is very simple now at this point. It merely needs to implement the class of order and allow the base class to take over the responsibility of performing the checkout. Now what this means is that if we decide that we need to change who our payment processor is, that responsibility no longer lives within any of these order classes. It's been completely abstracted away into a payment processor class. Likewise, if we decide to change how we notify our customers, that's in a separate method as well. And it's only even affecting the online order implementation. And the point of sale system will have no impact from changes to how we notify customers. So what are responsibilities? Responsibilities are stated simply as a reason to change. You can think of them as differences in usage scenarios from the client's perspective, where the client is the code that's making use of your code. Multiple small interfaces, which follow the interface segregation principle, can help you to achieve the single responsibility principle. And you could see from our refactoring that we ended up with 3 small interfaces that each had one responsibility, and it wasn't any concern of our order implementations how these were being achieved. And it made it so our order class had the sole responsibility of stitching together these other collaborators in our class and letting each of them do the job that they're responsible for. So to summarize, following the single responsibility principle can lead you to lower coupling and higher cohesion. Many small classes that have distinct responsibilities tend to result in a more flexible design. You'll find that if you follow this principle, a lot of the times you'll have very few if statements or switch statements or branching logic in your code because you've isolated the things that would act differently into separate classes that know how to behave in their specific environment, in their context. They have only one responsibility. They do it. There's not a lot of if checking to see whether or not they should behave one way or another. Some of the related fundamentals to this include the open-close principle and interface segregation principle, both of which are part of the larger SOLID acronym of best practices for object-oriented design. And it's also related to the concept of separation of concerns. I recommend reading Clean Code by Robert C. Martin, which you can get at the URL listed below. And I need to provide some credits to the images that were used for the motivational picture, as well as the single responsibility principle article from which the rectangle example came. Thank you very much. This has been a Pluralsight on-demand video for the single responsibility principle. Come back soon to find out more about best practices for writing object-oriented software.